is about how fast reactions go. So, the working theory that explains why rates change for chemical reactions is called the collision theory. So our explanation for why reactions go at different speeds and how we can change the speed of a reaction, speed it up or slow it down, all that's about come out of the collision theory. Okay? And the collision theory starts off with a really basic idea that in order to react with each other, the molecules have to touch each other. If they don't touch each other, they can't react. That's not a huge stretch, is it? Okay. But this is not called the touching theory. Okay. Go home to your parents and say, yeah, I was driving and my car touched another car. You're going to get a different reaction than if you say I was driving and my car collided with another car. Those are different things, right? So it's not called the touching theory, it's the collision. They have to collide. They have to hit hard. The reason why they have to hit hard is because they have to break bonds. The first step in doing a chemical reaction is getting the things that are already stuck to each other not to be stuck to each other anymore. Get them away from each other so that you can put them together in new ways. The first step in rearranging the atoms is to take the old atoms apart, away from each other. This is the whole theory. They have to hit hard enough to break the bonds. So anything that increases how often or how hard they collide with each other will make the reaction faster. Anything that increases how often and how hard, or that decreases how often and how hard, hit less often, less hard, it's going to slow the reaction down. Because sometimes we want reactions to go faster, sometimes we want them to go slower. Some reactions naturally go slow, rusting. Some reactions naturally go fast, explosions. We can speed those up and slow those down by changing how often the pieces collide. And so let me show you the graph that I've showed you in the past where we talked about endo and exothermic. We had a graph, we started here, we ended there. If it went down, it was exothermic. If it went up, it was endothermic. Okay? But actually, it doesn't go straight from reactants to products. It takes that path. And that path is a higher energy. Okay? And that's because, let's say I had H2, 2H2 plus O2. That they have to hit each other hard enough to break bonds so that they can be put together differently on the other side. So I got to hit hard enough so I can break the H's away from the H's and the O's away from the O's so I can put them together to make my H2O's. So the height of this hill is about how hard they had to hit. And that height is called the activation energy. The activation energy is the minimum energy to make a reaction happen. Now, this would be an exothermic reaction because I ended up lower. Okay? It's the kind of thing this graph would describe. This graph would describe what's happening in a Bunsen burner. If I just turn on the gas and the oxygen, I can fill the room up with gas and nothing will happen until I make a spark. And what the spark does, the spark gets the first one over the hill. And then it's going to release energy as it falls down from that hill, and that energy it releases gets the next one over the hill. And that's going to release energy, it'll get the next one over the hill. So you only have to spark the flame once, and it continues to burn. What you have at the top is called an activated complex or a transition state. It depends on who you're talking to. If you're talking to people who are worried about what the chemicals are, it's a transition state between the reactants and the products. It's in transition. It's the reactants becoming the products. The people who call it an activated complex are the people who study the energy of the reaction. So they're focused on the energy. It's complex and it's had the activation energy put into it. Activated complex just means it's ready to go. It's ready to react. Okay. So the activation energy must be supplied to start the reaction. Every reaction has an activation energy. If it didn't have an activation energy, the original pieces wouldn't have been stuck to each other to start with. Right? Because that activation energy is to break them apart. So what does it mean if a reaction has low activation energy? That means that hill is small. That they don't have to hit very hard in order to react. That means lots of collisions are going to be hard enough. And if lots of collisions are hard enough, you're going to have a fast reaction. So reactions with low activation energies are fast. Things with high activation energies. High activation energy, they have to hit each other really hard before they react. A lot fewer are going to hit really hard. So you're going to have a slow reaction. So the size of the hill tells me something about the reaction, whether it tends to be a fast reaction, tends to be a slow reaction. Okay, to try to give you the concept of activation energy, try this. Okay, let's see if I can get it to show up on the camera. Played with it, maybe it'll work. Okay, so here I've got a candle sitting on my thing. Why is the candle not on fire? It has everything it needs to have a fire. It's got fuel. It's got oxygen. Why isn't it burning? The collisions aren't hot enough, right? The collisions aren't hard enough. So how do I get that candle to burn? What do? You add fire to it, you light it, right? So me lighting the candle is supplying the activation energy. Okay? So the candle's burning just fine. Okay, now here I have a piece of wire that I coiled up in circles. So I just made a coil of wire. Okay? How to put it out? Did it stop the air from getting there? No, it's a coil of wire. Air goes right through it. But it put out the fire. I got to relight it. Just a coil of wire. Just put it over the candle. Doesn't work as well the second time. So how is it putting out the candle? Well, here's the key. Anybody want to touch this wire? It's hot, right? So the heat from the candle, what I did was I stole heat from the candle. Instead of using it to get the next one over the hill, it went in here. So they have to hit hard enough, but I stole the heat. So they weren't hitting as hard because the heat went into here, not into the candle. It's the same reason blowing your candle out works. You know, oxygen and candles make fire. It doesn't make sense that if you blow on a candle, it goes out because you're just giving it more oxygen. Why does a candle go out? Well, because you're blowing all the hot gases away. So if the hot gases aren't where the wick is at, the wick doesn't have the activation energy and the candle goes out. And that's how trick candles work. The ones where you blow them out and they come back on. They have a wire in the middle of the wick. So if you blow them out, the wire stays hot. And it supplies the activation energy to relight the candle. So to put them out, you got to make sure not just they're out, but you got them out and cold, which is tough to do with when you're full of hot air. So that's how the trick candles work, that you blow out and they come back on, because they've got something to retain the heat inside the wick. Okay? So got the idea of activation energy? They got to hit hard enough. Okay? Got to hit hard enough. So if the reaction is endothermic, you have to keep supplying the heat. Because the graph of an endothermic reaction, the products have to be higher than the reactants, but actually the activation energy goes up above that. So this reaction would have a really high activation energy, because you count from where you started to where you ended, which is the high part of the hill. So they got to hit that hard before they can react. And then after they've reacted, they give you back a little bit of heat, but that's not enough to get the next one over the hill. So you've got to keep supplying the heat. If it's exothermic, it releases energy. And that energy can be used to supply the activation energy to those that follow behind, which are going to give off enough heat to get the next ones to go over the hill, which are going to give the next ones enough energy to go over the hill, as long as I don't blow all the hot molecules out of the way. So exothermic reactions keep happening because they're heating their pieces enough so that the next piece has the activation energy to react and give off energy that gets the next one over the hill. Okay. But back to our graph. The overall energy change, the things we have been talking about reactions giving off energy, is starting versus ending. So this reaction would be exothermic because it ended up lower. Doesn't matter what path it takes. It ends up lower. So I bring my lighter to the candle. I give my lighter to oxygen and hydrogen like you guys did in your rocket. You made a spark. That spark got the first one over the hill. And it released enough energy to get the next one over the hill. And those released enough energy to get the next one over the hill until you ran out of oxygen and hydrogen. Which is why you should have had a stoichiometric mixture of 2 to 1, because it's 2H2 plus O2 makes 2H2O. So that's why there's different rates, because every reaction has an activation energy. So how can I affect those rates? What can I do to them? What can I change that will change how fast reactions happen? First thing I can change is the temperature. So remember, we said temperature was about molecules moving. That's why there's an absolute zero. Absolute zero is where everything would stop, right? So temperature is about molecules moving. So as I raise the temperatures, they're moving faster. And as those molecules move faster, there's going to be more collisions because they're moving faster. And those collisions are going to be harder because they're moving faster. So that reaction is going to go faster. This is the working theory behind your refrigerator. Why do you put food in the refrigerator? No, it's not to make it cold. Keep it from killing you. Is that a fair way of putting it? That if you just leave it on the counter, it undergoes chemical changes to make things that could kill you, at least make you sick, right? That the chemistry sitting on the counter changes. And those are all chemical reactions. So to slow those chemical reactions down, you put it in the refrigerator. Scientists use as a rule of thumb for most reactions that if you cut by 10 degrees Celsius, you cut the reaction time in half, or double the reaction time. So if you went down 10 degrees, it would take twice as long. Down 20 degrees, it would take four times as long. Okay? It doesn't work perfectly, but it works pretty well. So you put it in your fridge because you want to slow down the chemical reactions that lead to spoiling. Now, yeah. No. Microwaves heat up to the points where it will actually kill the germs that are making the poisons. Okay. Now, it speeds up those reactions that would kill the germs. Okay. But when you put it in the fridge, we've all reached that back corner and found that Tupperware container. Does it stop food from spoiling? It does not stop it from spoiling. It just slows it down. If you want to slow it down more, what can you do with that food? Freeze it, because that's even colder. And it's a solid, so they're not moving, so they can't run into each other. But you put things in the freezer, you should only leave them there for so long, because it doesn't stop the reaction. It just slows it down. Food still goes bad in the freezer. Okay. So the other thing, I talked about rusting. We think of rusting as slow, right? It take years and years. In Michigan, it happens a little faster because the salt lets electricity flow and lets the pieces touch each other a little bit better. But there's a cube in Saudi Arabia, big iron cube. It's been there for thousands of years without rusting. But that tells you rusting is slow. But ever watch somebody use cutting torches where they cut metal with torches? Okay, what you learn when you do that, because I learned how to do that, is that first you turn on the gas and the oxygen and you get the metal hot. And then once you start cutting, you can turn off the gas and just use the oxygen, and it will cut right through it because that oxygen is actually reacting with the iron. Oxygen plus iron makes rust. So in a cutting torch, it's happening as fast as they move that torch. whereas in Saudi Arabia, it's been there for thousands of years. Temperature can make a difference in how fast that reaction happens. Okay? So the cutting torches are actually oxidizing the iron. Yeah. It would serve as a catalyst, because catalysts are different. We're going to get to those, because catalysts did speed it up. We need to talk about why they did that today. So that's one of the things. So it's not a catalyst, because the catalyst is the stuff, and temperature is motion. It's movement. Okay. So makes sense that temperature is going to affect rate. Yeah?
So does like the activation energy have to deal with like trying to start a lawnmower with?
If you're trying to start a lawnmower, you got to get that right mixture of gasoline and fuel and the spark all at the same time. If one of those three pieces doesn't show up, you don't have a lawnmower. Okay? But on a lawnmower, every time the piston goes up, every other time the piston goes up and down, they make a new spark, because they stop the reaction in between. So it starts, goes fast, and then it stops. It's done. You used up all the fuel. It pushes the exhaust back out, opens back up, draws in more fuel and oxygen, squeezes it, and sparks it again. Okay? And the squeezing it affects the second piece, concentration. Concentration is a measure of how close things are to each other. So the more concentrated something is, the closer together the molecules are. So how's this going to fit into collision theory? If the molecules aren't close together, how's that going to affect collisions? There's going to be a lot fewer collisions. If they're concentrated, if they're closer together, they're going to collide more often. So the more concentrated they are, the more often they hit, the faster the reaction goes. Okay. So to show you that, I'm going to do the lab you guys have done a couple times. Okay. In order to generate the oxygen for your rocket, you can decompose hydrogen peroxide. And in order to the heat of the reaction, we measured hydrogen peroxide. So, is that on? Oh well, it's off in a second. Okay, so we took hydrogen peroxide, and hydrogen peroxide they put in a brown bottle because the light will make it react. Okay, light will make it react, but we don't have time for the light to make it react, so I'm going to put in the catalyst that we used, manganese dioxide. So I put in that catalyst, and that reaction happens. And we've seen it happen. So the catalyst speeds it up. We've got to figure out why a catalyst does that. That's going to be later. But it released oxygen. So the concentration of oxygen in here is high. Right? So if I light a toothpick on fire and then blow it out, it burns better in oxygen. It burns faster in oxygen. But that oxygen makes it burn faster. Higher concentration, faster reaction. That being said, this is 3% hydrogen peroxide. This is 30% hydrogen peroxide. They put it in that expandable bottle in case something goes wrong and it makes gases, so it won't blow it up. You can't order this. I get it from Flynn Scientific Company. They ship it to the school address. They don't ship it to any place but school addresses. Okay. And this reaction happens a little faster. 10 times as much hydrogen peroxide, but it's already done reacting. This one's still bubbling. 10 times as much stuff, but this one's still bubbling. More concentrated, faster reaction. But there's a trick to this too. I got to be careful when I pick this bottle up because this is hot. Okay, we use this as an exothermic reaction, right? So what happened is the catalyst sped up the reaction, which gave off heat, which heated up the solution, which made the reaction go faster, which released more heat. So that cloud you saw climbing out was steam. It was actually boiling the water. It was a cloud of steam. Okay. More concentrated, fast reaction. That's the working theory behind what we do if we spill acids on ourselves. What do we do if we spill acids? Put it underneath lots of running water for a long time. Because if I make the acid less concentrate, it's going to react with me slower. Which is, I'd rather not react with me at all, but if it's going to react, I want it to do it slow. Okay. Particle size. Particle size affects rate. Molecules can only collide at the surface. Well, yeah, I can't. In the middle of a clump, the one in the middle can't hit anything else because it's in the middle. So the smaller I make the particles, the bigger the surface area. So if I take a big piece and cut it in half, now I've just exposed two new pieces that weren't exposed before. Every time I break it, I expose new surfaces. So if I grind it up, I get new surfaces. So the smaller I can make those particles, the faster the reaction's going to go. Small particles, faster reactions. To show you that, here I have this powder. It's called lycopodium powder. A little pile on the desk. Yeah, it's piled up, but okay. So lycopodium powder. I picked it simply because it's a flammable powder. Okay, because that's what I'm going to do. I'm going to light it on fire. Yeah, see if I can turn that light down a little bit. Okay, so there it is on fire. Okay, if I want to make that fire bigger, I need to stretch it out. Okay, the problem is the ones at the bottom can't burn until I bring them to the top. Right? Until the ones at the bottom hit the top, they can't burn. So if I can pick some off the bottom, I can make it burn faster. Right? The more I spread it out, the more surface is in contact, the faster it burns. Make sense? Now, if there's just a way I could really spread it out, like that. Okay. Now, that was hard to see, so let me try a different way. Oh, yeah, it's a little flame in there. Put it out. Oh, the tables are heat resistant. You got to get these tables have to get up to about 2200 before they melt, because I've melted a couple. That's how I know. So I know what not to do because I've melted it a couple times. Okay, so I'm going to take some of the powder and I'll put it in this funnel, and that funnel is going to give me a way of really spreading it out. Burned faster, didn't it? A little bit faster than that pile on my desk, right? Why? Why was it faster coming out of the funnel? Yeah, because it was mixed with air, and the powder had air all around it, right? So every little tiny piece of powder had air all around it, so it could react on all sides, versus the stack where it could only work on the top, couldn't work on the bottom yet. So by spreading it out, I let it react really fast. Now, what would happen if I inhaled? I'd get a mouthful of powder because the flame's out here. I got no activation energy. Right? There's no activation energy, so I just get a mouthful of dry powder.
Oh.
Okay, so didn't burn it up. No, it burns out so fast. You keep. Okay, so by tearing it into individual tiny powder particles, I can make it burn really fast. This actually causes a problem in manufacturing and agriculture. Because when they take, in agriculture, say they get some wheat, right? And they fill the silo up with wheat. That means that wheat moved through a conveyor belt. They filled it up through the top so the wheat was rubbing against itself all the time it was moving through. And it breaks off little tiny pieces of chaff. So that when they empty the silo, a cloud of dust builds up inside the silo. And if there's a spark, the silo blows up. And by silo, I mean 20 stories of concrete. Big silos blow up because dust is a dangerous thing because it can burn fast, because it can burn on all sides. Coal miners have to worry about it, coal dust. If you look at anybody working a coal mine, you'll see that where they're grinding the coal out, they're spraying it with water. Because if the mine fills up with coal dust, that's going to happen. And you don't want to be in the middle of it. It's bad enough being next to it when it happens. Imagine if you're in the middle of that when it happens. A, it's hot. B, when you're done, there's no oxygen. Right? So, dust explosions are dangerous. But dust is not the smallest we can go. We can make things smaller than dust. Individual molecules or ions. That would be the limit of how far we could tear things down. And how could I tear something into an individual molecule or an individual ion? Dissolve it in water. Dissolving tears it up into individual pieces. Those individual pieces have nothing between them and the other piece they have to touch. So dissolving speeds up reactions that would happen too slow, and that's why they look for water on other planets. Because water dissolves lots of stuff. And unless you can dissolve it, they can't figure out a way that the reactions for life could happen fast enough. That the reactions would just be too slow if you can't dissolve it. Because think about what it would take to get two solids to react with each other. You take this solid and that solid and you make them run into each other. Boom. Where they touch each other, they react. But now they're not touching each other because there's product in between. Where they touch, they made product. There's products in between. They're not touching, the reaction stops until you get rid of that product in between so they can touch each other again. It's going to be slow. So if you think about collisions, these all make sense. What collisions cause reactions and temperatures about how fast molecules are moving. With those two pieces, each one of these makes pretty easy sense. How often are they going to hit each other in that situation? Okay, different is the fourth thing that affects it is different. And that's the catalyst, the one thing we've talked about all year. Catalysts speed up the reaction without being used up by the reaction. when I write the equation for what happened in the labs, it was H2O2 makes H2O plus O2, and the catalyst MnO2 went over the arrow. Because it wasn't a reactant, it wasn't a product. All it did was speed up the reactions. So, is putting in a catalyst going to make it run into each other more often? Is it going to make them run into each other harder? Oh, so it doesn't seem to fit with our collision theory. Okay, but it does. What it does is it changes how hard they have to collide. It gives us a new path, a new way for this reaction to happen, where different pieces touch each other, and the new path has lower activation energy. It changes not how often they hit or how hard they hit, it changes how hard they have to hit. It makes those bonds easier to break. Remember what enzymes did? They actually stretched bonds. It hung on to molecules and stretched them a little bit. Helped break that bond. And if you're already helping break the bond, you need less activation energy, and more of those collisions are going to have that much energy. So it changes how hard you have to hit. More pieces are going to be hitting this hard, so the reaction goes faster. Now, related to enzymes are inhibitors. Inhibitors block the catalyst. So if your reaction's been sped up by a catalyst, the inhibitor is going to slow it down. If the reaction hasn't been sped up by the catalyst, inhibitors will have no effect. They don't slow the reaction down, they stop the catalyst from working. And most of your DNA codes for enzymes and inhibitors. It doesn't code for the molecules you want. It codes for molecules that codes enzymes that make those molecules faster. Because that's more efficient. A little bit of DNA can affect a lot of molecules versus that one DNA to one molecule is too slow versus one DNA to enzyme to lots of molecules reacting. So the way you achieve homeostasis is by putting in enzymes when you need a reaction faster and inhibitors when you want to go slower. That's what DNA does. Homeostasis is where everything's at constant even though processes are going on. So this is what a catalyst does to our graph. Makes the hill smaller. More pieces are going to have enough energy to get over that hill. So it changes how hard they have to collide. So this much energy is going to be more attainable than that much energy. So chemists are always looking for enzymes and catalysts to speed up reactions. Favorite one I read about was the U.S. Navy has come up with a catalyst that lets you take carbon dioxide and water and make jet fuel and oxygen. So they can make their own jet fuel out of the water in the ocean and the carbon dioxide in the air. And so it takes a huge amount of energy. You need a nuclear power plant to do it. Our aircraft carriers have nuclear power plants. So they can make their own jet fuel. So they're trying to do that so that they don't have to have tankers follow them around. because if you want to stop planes from attacking, you don't have to hit the planes. You only have to hit the tankers, because if they don't have any fuel, they don't fly. So artificial photosynthesis. CO2 plus H2O making stuff. Artificial photosynthesis. A few questions on that tonight.